All right, welcome back again, everybody. Today we're going to be doing section 16.6, which is a pretty fun section because we get to learn all about parametric surfaces and how to compute their areas. So it's a fun section, and it's going to lead us very directly into the next section, actually, when we talk about surface integrals. And you'll see that a lot of the stuff we do in the next section, 16.7, is very much built off of what we do in this section. So it's kind of nice. Let me pull up the slides, and we will get started. Okay. So here's the overview. We're going to introduce what parametric surfaces are. Then we'll actually talk about surfaces of revolution and how to describe those parametrically. Then we'll find out how to determine tangent planes to parametric surfaces. We'll compute the area of these surfaces. Then we're actually going to recover the formula from section 15.5. That was the section that I skipped. So we didn't actually cover section 15.5. And the reason is that you can get the same formula with a more general theory. So I held it off until this section now. Then at the end, I'll give you some helpful Mathematica commands, but I'm actually going to pepper those throughout the lecture, so that won't take very long. Naturally, you can graph these things using Mathematica and other software. Mathematica also has commands that are built in to let you compute surface area, so we're going to take a look at those. And for the activity, we will actually be meeting in the computer lab, and we're going to mess around with Mathematica and graph a whole bunch of different kinds of surfaces. Even a Mobius strip, an example of a non-orientable surface. Okay, so here's where we're going to begin. So what we're going to do is we're going to extend our ability to describe more general surfaces using vector functions. That's essentially what this is. We've already seen surfaces that are the graphs of functions of x and y. So for example, z equals f of x comma y. We've already seen these types of surfaces. We've also seen surfaces which are level surfaces of 4D objects. You basically just fix this, this value and then you get a level surface of this three-dimensional function, which is really going to be a surface on a four-dimensional object, or like a single surface, you could say. So more generally, we can describe a hypersurface as the image of a vector function whose scalar component functions are multivariable functions. That's basically the setup. This is a natural generalization from what you might remember about space curves. So if you remember when we talked about space curves way back in chapter 12, we described a space curve using a vector function, but it was a vector function of a single variable, t, right? So because a surface is two-dimensional, we essentially need two variables to describe the surface itself. So what we're going to do instead is we're going to create a vector function that is two-variable, and our parameters are going to be u and v, and the thing that is described by this vector function is going to be a surface in R3. That's the basic idea. So let's see the setup here. We're going to define our parametric surface using this function right here. So it is a vector function. R is a vector function. You put in the inputs u and v, and what you get out is a vector. And here what's happening is each one of these component functions is a scalar function in terms of u and v. So you have a function that's describing the behavior in the I direction, a function that's describing the behavior in the j direction, and a function that's describing the behavior in the k direction. And each one of those functions is a function of u and v. That's the basic idea of it. So what is the surface itself? The surface is the set of all points in R3 that are, or the vectors, the position vectors are the images under this mapping right here. Our parametric equations are given by these. And the surface that's described by this vector function is what's called a parametric surface. And these are the parametric equations. All right, so here's a picture that kind of shows what's going on. We've got a parameter domain, call it D, and D is in the UV plane. And what we're going to do is we're going to apply a vector function of two variables to this region, and it's going to map this region to some surface in space, just like this. So you could even kind of think of it as taking this flat, blob and contouring it in space in some way. And then what this function gives you is the position of any point on the surface, just like so. Okay, so let's do a couple of examples. And these ones I think you can probably do on your own. So try to do this one first. Identify and sketch the surface that's given by this vector function right here. It might look a little bit familiar, so take a minute and think about what it could be describing. And then, as always, you got to say something out loud to your friend, to your colleague, your cat, your dog, to yourself. Just say something out loud. And now try to sketch it, or at least write down what you think it is. What surface is described when the behavior in the I direction looks like this, the behavior in the J direction looks like this, and the behavior in the K direction looks like this. Okay, so for this one, the first thing that I notice is that in the I and K directions, you've got this cosine sine behavior. So there's something circular going on in these two dimensions right here. And then in the J direction, you've just got a linear function. So things are scaling linearly with a scaling factor of 1, essentially, or whatever V is going to be. So putting all this together, this vector function actually describes a cylinder, right? So X is 2 cosine U, Z is 2 sine U, so you've got this circular behavior in the XZ plane. And then Y is just V, so you're just kind of extending in the Y direction. And then you've got a cylinder whose axis is the Y-axis and the radius is 2 because these coefficients are 2. So this is a vector function that describes that cylinder. All right. Now, there's a particular set of curves that we are interested in when we talk about parametric surfaces. So if we've got a parametric surface S, we are particularly interested in what are called the grid curves of S. And the grid curves they're generated by generated when you hold one of the variables fixed. But the basic idea is this. How do I say this? Well, okay. So these curves correspond to vertical and horizontal lines in the UV plane. But I feel like this is a little more descriptive right here. So more specifically, what we're looking at is the images of the vertical and the horizontal lines under the mapping R. So essentially do this. Yeah, here's an example. Fix U equals U naught, where U naught is just a constant. Then our vector function becomes a function of a single variable. So we're holding U naught fixed and we're letting V vary. So this is now a function of a single variable, a vector function of a single variable. And so that's describing a space curve, some curve in space that lies on our surface, right? But when we fix U as this constant, what we're really doing is we're looking at a specific line in our parameter domain, right? And then we're looking at where that line gets sent to under the mapping R. Here's a nice picture of it right here. So let's say D is our parameter domain right here. And if we fix U equal to some number U naught, then what we've really done is we've restricted our attention to this vertical line that you see right here. And then under the mapping R, this vertical line, this pinkish one, gets mapped to this space curve that you see right here. There's the corresponding image of this line. So you take a look at this vertical line, you run it through R, and then R spits out that space curve. Similarly, you can fix V, right? So if you fix V equal to V naught, then you're focusing all your attention on this horizontal line, mapping it with R, and then what you get is this green space curve right here. So it makes sense why they call them grid curves, right? Because these are essentially these these grids from the UV plane being mapped to these grids on our surface that are actually on the surface itself. So the grid curves are really handy because they can essentially tell you how the surface behaves in a particular direction. So they're good to look at and try to make sense of. We'll do that in just a minute too. All right, so here's an example. This is one I definitely want you to think about and try on your own, and then we're going to take a look at it in Mathematica just to build some intuition for it. So here is the vector function. R of uv is given by this vector function here with these component functions. Here's the first one, here's the second one, and then here's the third one. So first thing I want you to do is just look at this and think about what object it could be describing. Give yourself a minute to kind of process what it's saying. Okay, now say something out loud to yourself. And what I'd recommend is try to say out loud to yourself what is happening in each component direction. Like what's happening in the I direction, what's happening in the J direction, what's happening in the K direction. Okay. And now see if you can describe what happens when the grid curves, the different grid curves are fixed. So what happens if U is fixed? And what happens if V is fixed? What space curves are being described under those fixes? All right, here we go. So we'll explore this more in the activity, but just to give you an idea, this is what it looks like. It's this kind of spirally tube. It's actually, yeah, if you like pasta, this is actually a cavatappi noodle. So if you ever buy those at the store, this is the mathematical description of that particular noodle. So now when you see cavatappi, you can be like, oh, I can describe that mathematically. So keep an eye out for it next time you're at the grocery store. Now we're going to look at this again in Mathematica for a minute here, but this object here, it's got circular cross sections. If you were to chop the noodle, right, you'll get a circular cross section. And those are what you get when you fix the number u. So when u is fixed, in particular this, and this, what you get is you get a circular cross section. Now, if you fix V, so if you fix this and this and this, what you get is you get these spirals. So I don't know if you can see it here. I'll show you in just a minute. You get these spirals right here. And those are the spirals you get when you fix the V variable. Okay, let's take a look at it in Mathematica. You can use this plot command, vector plot 3D, and you can graph these things. We've looked at that before, but let's take a look at this one again. All right. Where'd you go? Where'd you go? Oh, there it is. Okay. Right. Yes. Okay, you can see this. So here is the command that's plotting our cavatappi noodle, parametric plot 3D. All I did was I entered the vector function like so as a list. There's the vector function entered as a list. And then I specified where u was going to go from and to, and where v was going to go from and to. And then this is what it produces here. There it is. Look down on it from the top, you can see it's like a spiral slide, right? So those of you that want to go on to engineer like playground equipment or water slides, you'll get to play around with this stuff. There you go. The world's most interesting water slide. It's a cavatappi noodle. And again, you can mess around with the parameters to see what happens when you have it not go on so long. So check it out. Like if I drop this down to 2 pi, it shortens it, right? And this kind of makes sense if you think about, actually here, let me look at it from the top. See, if I look down on it from the top, that's one full rotation, one full rotation. That's why we got like one loop, you could say. So U is essentially letting you go whoop, up like that. And V is kind of going around and around and around as you go up. And that makes sense too if you think about this Z component function right here, because U is being treated linearly. So U is just going to let you go up and down in the Z direction. But this cosine V, that's going to give you vertical wiggling as you go up and down. So maybe if I can kind of do it like this. So U is what's going to send you from like bottom to top, right? You would go like up as U increases. But this cosine V bit right here, that's going to make it go woo, 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 and you're going to get these like spirals or these circles. And that's why you're seeing the circular cross sections, right? So mess around with that some more if you'd like. You can get this on Canvas as well, or you can just open up Mathematica and put this in yourself. But let's get back to the slides. All right. Okay, let's do another example. And this one is important, and it's also very nice. It's very natural and very nice. I want you to try to find a vector function that represents the plane that passes through the point P naught with position vector R naught, and it contains two non-parallel vectors A and B, right? So this is one I definitely want you to think about on your own for a minute. Okay, now say something out loud to yourself about what you think this vector function would look like. Anything just to get you started. All right, now try to work it out on your own. See if you can produce a vector function that describes a plane that contains this point P naught and also contains two non-parallel vectors A and B. And then we'll do it together in just a moment. Right, here we go. Okay, so first thing is this. We need some kind of parameters, right? So we have this point P naught that basically gives us an initial starting point, right? And then we know that the plane also contains these two vectors, but we can scale those vectors by any amount that we want. So any vector in the direction of A must have the form u times A, where u is a scalar. And any vector in the direction of B must have the form VB, where V is a scalar. And U and V can vary, right? So if this is the vector B, VB lets you stretch this vector out. So you can shrink it or you can stretch it out any length you want. That's essentially what V is doing, scaling things. Same thing with A. So here's the given vector A. And we can scale A by U, and when we do that, it's essentially stretching it out or compressing it, or even turning it around, right? Like if U is a negative number, then it would go like so. Now, that means that for any point on our plane, so here's a secondary point on our plane. Here's the initial point that we're given, right? What that means is that we can describe the vector that goes from P naught to P as a linear combination of these two vectors, A and B. And that's what's happening right here. So this vector that you see right here, P naught to P, you can write it as a scalar multiple of A plus a scalar multiple of B. That's a vector sum, right? So that's how we're describing this, as a linear combination of A and B. Okay, and we can do that for any point. So that's the thing. We can do that for any point P on that plane. It doesn't matter what the point is. So to describe the plane, all we need to do is talk about getting to the point P naught and then going some amount in this B direction and some amount in this A direction, and that'll describe any possible point on that plane. So in a formula, it looks like this. R of u comma v, I should say, is starting at the position r naught, and then you can go along this vector to any other point on the plane. But the vector p naught p is this sum of these two vectors right here. And so this is the formula. That is the formula. So we can write the vector function for this plane as this. R of u comma v equals your initial point plus go u in the A direction and v in the B direction, and that will take you to where you need to be. I do say real numbers here, although really I should say scalars more generally. For us, we've only been working with real numbers, but these can be any kind of scalars. Okay, now that we have the vector function, we can recover the parametric equations for the plane. So we make some basic assumptions here. Let's let r be x, y, z. R naught will denote by x naught, y naught, z naught. So that'll be the point p naught, written in vector form. We can say that A has the components a1, a2, a3, and B has the components b1, b2, b3. So then when we use our vector function representation, we can glean the parametric equations like so. And this is where I want you to take a moment and just realize how like naturally generalized this is from the parametric equations for a line, right? When you had the parametric equations for a line, it was essentially the same structure, except you didn't have this second term, or maybe I'm sorry, we should say third term. You didn't have this third term, right? You just had the initial point, and then you had one set of direction numbers telling you which way to go so you could travel along that space, that line, right? That line in space. Well, now we have two separate, or we have not two separate. Now we have two descriptors to describe where to go. And that will keep us on that plane. And we're describing every point on the plane with these equations. Just like so. All right. Okay, another example. This one you should definitely be able to do on your own. So try this one on your own. See if you can find parametric equations for the sphere centered at the origin with radius a. So ponder it for just a minute. Then say something out loud about what you think you might use. Right, and now find the parametric equations for that sphere of radius a centered at the origin. All right, okay. Well, since we are describing a sphere and we're trying to do it parametrically, I think the natural choice would be spherical coordinates, right? So earlier on in chapter 15, we found the formulas for spherical coordinates and converting from Cartesian to spherical, right? So we can use those parameterizations to describe a sphere parametrically. So if you remember, x was it was rho sine phi cosine theta, and y was rho sine phi sine theta, and z was rho cosine phi. And in this case, because we have a fixed radius, we're setting the radius equal to a, rho is just going to be a. Rho is not going to vary in this case, right? So we get this, this, and this. Then we can write our vector function as simply using these as our component functions. So r of phi comma theta is this times I, this times j, this times k. And that's the description right there. Right. Now, one thing that is cool about this is this. This parameterization is essentially describing how to convert a rectangle in the phi theta plane to a sphere in space. And those functions are deforming this rectangle into this sphere. And what really helps is to look at the grid curves, right? So let's do this for a minute. Which one do I want to start with? Okay, let's say we fix phi at this number c. Remember, phi is like the angle that you have when you tip down from the z-axis, right? That's what it's describing. So if we fix phi at this value, we're essentially fixing ourselves at one angle down from the z-axis, right? So one angle measured down this way. And once we fix that angle, oops, sorry. Once we fix that angle, this curve gets mapped to this circle that you see right here. That's what's happening. So this line is getting mapped to this circle under this parameterization. That's exactly what's happening. And that's true for any one of these fixed lines. So anytime you fix phi, you're going to get another circle, like a circle of latitude, right? And there's a bunch of them. There you go. So that's what the grid curves look like when you fix phi. Now let's fix theta. So now change your perspective to look at theta. Theta goes from 0 to 2 pi. And if you remember, theta is going to lead us around like so, right? Wait, did I go the right direction? Yeah, I did. Theta is going to lead us around like this. So when you fix a value of theta, maybe here, you're basically fixing an angle that you're turning. You're going to fix it like right here, let's say. So in this case, this is the fixed angle. And then what you do is you let phi vary. So phi is going to go up and down. And that's why you get this. Can't quite show you the bottom, but there it is. That is corresponding to this fixed line right over there, from here to there. And that's it. So when you look at the sphere, you can think of it as a rectangle that's been pulled together in just the right way. Maybe more specifically, what the way that you're getting this sphere from this surface right here is you're identifying, here, let me do colors here. You're identifying these two edges. We're going to do a little bit of topology here for just a minute. There you go. You're identifying these two edges. So you essentially curl them together, and then what you have is you have, actually, let me do it this way. Nope, that's not what I wanted. There. Let me start with this. You're starting with this. And when I identify those two edges, when I glue them together, literally glue them together, that's going to correspond to this line right here, we'll say. So we take this, and we stitch them together right here. That's what's happening there. The next thing we do is we're going to take these lines, so this edge right here, we're actually going to shrink this edge to a point. So quite literally, it's taking this circle that you see here and squeezing it down to a point. Maybe you can imagine doing it physically, almost like you were, almost like wrapping a piece of candy or something, right? So if you squeeze this together and squeeze it down to a point, you're like pinching off the top. Then you do the same thing for this line down here, which corresponds to this circle. And you basically squeeze it until you get a point. And when you squeeze the top and you squeeze the bottom in just the right way, you get a sphere. There it is. So now what you have is this, and then there was this. And there's your sphere, produced from a rectangle using this deformation, you could say. All right, cool stuff. Let's move on. One of the reasons that it's nice to have these different parameterizations of these types of regions is because it can give you simpler, we talked about this before, simpler or more natural representations of these objects, right? Now, you might even ask yourself, well, who cares? If we've got a representation, why can't we just stick with the one representation? Well, here's a good example. So look at these two images right here of a sphere. Both of these are generated by computer. This image is generated by solving for z in this equation of the unit sphere, and then graphing the top and the bottom separately. So that's what's happening there. So quite literally, if you solve this equation for z, you're going to get two. You're going to get one for the top when z equals the square root of 1 minus x squared plus y squared, and then the bottom, which is negative square root of 1 plus x squared plus y squared, right? And what's happening is this. Oh, I'm sorry. And then this one, what we're doing is we're graphing it using the parametric equations we found just a moment ago, using the spherical representation. So here's what's happening. The reason that this one looks all jagged and messed up around the edge is because, well, computers can't see infinity. They can only approximate things. And what we're doing is we're trying to have the computer approximate a rounded shape with flat planes, right? So imagine imagine each one of these little pieces you hear, each one of these patches is a flat plane. Well, what happens as you get close to this boundary circle, right? There's a boundary circle, oops, right in the middle here. What happens to the planes as you get closer and closer to that boundary circle? Well, they start getting, see if I can, they start getting straight, right? Well, that's a problem because when they get straight, that means that the tangent is basically, has no slope. So what's happened, the normal vector is pointing out right this. So we are asking the computer to approximate with planes that are getting more and more and more vertical as you approach this boundary circle. And it can't do it. It can't do it. It's only approximating, right? So the closer you get to this circle, the more garbage you get going on right at the equator right there. Now, that's not the case when you use the spherical parameterizations that we saw earlier. We're not asking it to use tangent planes that are getting more and more vertical. We're having it use tangent planes that are with respect to the other variables, phi and theta, right? And phi is basically an angle, and theta is an angle. And that's why you get this much, much nicer, unbroken picture. So what I want to do now is I actually want to take a look at these things in Mathematica so you can really see the comparison. Let me pull it up right here. So here's this one, and I'm going to use a couple different functions. This one I use contour plot 3D, and I also use plot 3D in just a minute. So contour plot 3D looks like this. So here is the positive one, square root. Oh yeah, square root of 1, yeah. And x is going from -1 to 1, y goes from -1 to 1. And as you can see, you get that artifacting right here near the boundary for the same reason I was just describing. It can't really handle it very well. And you get all this garbage from the approximation method when you get to a point where the tangent is nearly vertical. Yeah, the tangent is nearly vertical. Now, this one, because it's contour plot 3D, what it's really doing is it's looking at a level surface of a 4D object. So that can cause some more issues here. But we can also just use plot 3D because this is just a function of x and y. And plot 3D looks a little bit better. So when we use plot 3D, this is the image it produces. But if you look closely, near the edge, you can still see all this rippling, right? Uh-oh. You can see this rippling going on. For the same reason, it's still trying to approximate with planes, and it's having a really hard time when the planes start to get nearly vertical. And then just for fun, I also did the underside. So when I used contour plot 3D for the lower half of the sphere, wow, look at that. Whole bunch of issues. You can still see here we go. Oh man, I got too many things running on my computer. I should quit some. Okay. Oh no. Yeah, so this one, it's really, really having a hard time processing this image because the approximation method is giving you all these artifacts right here. Here it is using plot 3D. Again, it's a little bit nicer, but you still get those waves right at the equator. Now let's look at what it looks like when we use our spherical parameterization. Boom. There it is. And this is it, right? So this is the parameterization. Sine v cosine u, sine v sine u, cosine v. And remember, in this case, rho was just one. Did we do one? Yeah, for this one, for this picture, it was just one. So the radius of the sphere is one. And then u goes from 0 to 2 pi, that's the full rotation. And v goes from 0 to pi, that's phi, giving you this. So each one of these little patches you see here are approximations using planes, right? But you get a nice, relatively smooth approximate picture. Okay, I'll save this command for later. This one we're going to come back to later on in the lecture, but I wanted to show you why these different parameterizations can be helpful. Okay, let's do this example. So find a parametric representation for the surface z equals 2 times square root of that stuff. This is the top half of the cone. Oops, wait a second. Oh yeah, this is the top half of this cone. So this one I do want you to try on your own as well. So think about it for a minute. Right? And now say something out loud about what you could do to start, what's going to help you out, something like that. Okay. And now try to work it out on your own. Your goal here is basically to produce a vector function. Produce a vector function that describes this cone. Little hint, there may be more than one. Right, here we go. So the hint was a big one because there actually are more, there's more than one way to describe this cone. We have some choices. So the first choice is we can use a Cartesian parameterization because z is a function of x and y. So we could just literally let x and y be our parameters and then let z be given by this function of x and y. So that's one way to do it. So our parametric equations are this, this, and this. And if we write those as a vector function, we get this, just like so. X, Y, and then Z, right? So that's one way to do it. We could also do it using a polar representation. We just have to convert everything to r's and thetas, right? So because z is equal to this, and we know that I'll just say this, x squared plus y squared is r squared using that isomorphism equation, we get this, z is equal to 2r, and x is equal to the good old r cosine theta, and y is r sine theta. So now we can write this in a polar representation. R of r comma theta is r cosine theta I plus r sine theta j plus 2rk. And that's another equivalent representation of the cone using two different vector functions. Okay, so I hope this is kind of settling in and clicking. The next thing we're going to look at is surfaces of revolution. And what's cool is that these surfaces of revolution also have very nice representations using vector functions. And that's what we're going to look at right now. This picture will be a big help. One thing I will say is that the formulas will change depending on which axis you're rotating around. So just be aware of that. And think about everything you learned when you had to do surfaces of revolution back in Calc 2 or Calc 1, depending on where you went. All of that still applies, except now we're just going to describe these things using vector functions. That's it. So let's let S be the curve generated by the surface generated by rotating the curve y equals f of x about the x-axis. So this edge that you see here, that is the function y equals f of x, all right? So now what we need to do is we need to describe that surface, and what we can do is use right triangle trigonometry. So if you think about it, we can find coordinates or component functions in each direction to describe which way you should go in each direction. And here they are right here. Because our function f is a function of x, we can let x just be x. That's our first parameter. And then here, if you look at the picture, we can describe y, so this direction, y as our function times cosine theta, where theta is the angle. And you can see it right here. Let me zoom in a little bit, sorry. There we go. Okay, so here's our angle theta tipping up from the xy plane. And this length right here, or this displacement right here, is f of x cosine theta, right there. And then this displacement right here, that's f of x sine theta. Why? Because our radius is f of x. Our radius function is f of x in this case. So you're really just using right triangle trig, right? And you're getting r cosine theta, r sine theta, except now r is the function f of x, and that's it. So altogether, this is the vector function for a surface of revolution when you rotate it around the x-axis, the x-axis. If you had to rotate it around the y-axis, everything would structurally be the same, except this would be y, and this would be f of y cosine theta, and this would be f of y sine theta, for example. So there's flexibility. Oh yeah, and this would be a y also. All right. So those are quick, not too difficult. Now let's talk about tangent planes to parametric surfaces. This one is nice because you can probably guess how to do it. We've seen this kind of technique before, and we are going to see it again later in this section and also in the next section, 16.7. So what we would like to do is we'd like to find a way to compute a tangent plane to a surface that is described by a vector function, described parametrically. And it doesn't necessarily have to be a function where z is a function of x and y, right? So let's just start with a more general surface generated by this vector function, r of u of v. And what we want to do is let's find the tangent plane to this point on that surface. And the way we do it is similar to what we saw in the past. Remember, if you want to describe a plane, you need a point on the plane, and you need a vector that is normal to the plane. So the easiest way is to find the normal vector to the surface at that point. So if you can find the normal vector to the surface, then it's going to be normal to the tangent plane itself. All right, so this should sound very familiar. So let's pick a point P naught with this position vector, r of u naught comma v naught. We're going to fix u for just a moment here, fix u naught. Then once again, we have a vector function of a single parameter, and it defines a grid curve on C1, just like we saw earlier in the lecture, right? So you get this grid curve, and then what we can do is we can compute the partial derivative of r in that direction, right? So the tangent vector to C1 is the partial derivative with respect to v, this little arrow you see right here. So take your vector function r and differentiate it with respect to v. Boom, boom, boom. And that will give you this tangent vector. Do the same thing by fixing v equals v naught. Yeah, fix v equals v naught. And then this right here, this tangent vector, will be the partial derivative with respect to u. So you compute that. Boom, boom, boom. All right, now hopefully you can see where this is going. We've got two tangent vectors that are in the tangent plane. And what we really need is we need a vector that is normal to that plane. So what are we going to do? Take the cross product. We are going to take the cross product of these two vectors. Both of these vectors lie in the tangent plane, so their cross product is normal to the tangent plane. So this is what we need to compute. As soon as we compute this cross product, we have our vector. We have our normal vector. We already have our point, so we can describe the plane. There we go. Yeah, I guess I just left it at that. Okay. Wait. Oh, yeah, okay. Yeah, we're gonna do some examples in just a second here. All right, so now that we have this notion of how to compute a tangent plane at a point to a surface given by some vector function, we define this notion of smoothness. So we say that a surface S is smooth if this cross product is not zero anywhere on the surface S. So in other words, what we're saying is that the surface has no kinks or corners or cusps. You can think about it similarly to differentiability, where you don't want to have any like corners or edges or like cusps, that look kind of like that. You don't want any of those. That would not be a smooth surface. And intuitively, you can think of it as, if you run your hand over it, you're going to feel like an edge or like a point. That's not smooth, right? That's the idea. Okay, so now I want you to try this one. You have the basic idea. If you want to find the formula for the tangent plane, you just need a point, and you need a vector normal to the surface at that point. All right, so try to do it for this surface. The parametric equations are given here. Here is the point, and I want you to try to find an equation for the tangent plane at that point. So think for a moment about what you might do. Right? Say something out loud about what you're going to do. and then try to compute it on your own, and we will do it together in just a moment. All right, here we go. Well, we've already got our point, so we're good there. Now we just need to compute the partial derivatives with respect to u and v. Um, Not too hard. Partial derivatives are pretty straightforward. This is what we're going to get for r sub u. This is what we're going to get for r sub v. Then we're going to take their cross product. So we take their cross product. You can use that determinant notation there. And when you go through that whole process, you get this as the cross product. So what's nice is that this formula here will give you a vector that is normal to the surface at every single point on the surface. All right, we're going to see this again when we get to the next section when we do surface integrals. It's the same idea. You're going to see it pop up a whole bunch. This vector is normal to the surface that we're given. Right, so now we've got a normal vector. We have a point. At that point, this is what the normal vector is going to look like. How did we find that? Well, we just subbed in the values for u and v at that point. So the point 113 corresponds to when u equals 1, v equals 1, and then z equals 3. So 1 plus 2 gives you 3. So you plug those values in. Oh, wait, did I? Oh, yes, they're both 1. So u, oh, geez, I forgot. U, v, and then uv, I believe. I think that's what it was. So that's our normal vector. Thus, an equation of the tangent plane is this. Not too bad, huh? Pretty nice. There it is. There's our normal vector, and then there's our point. We've got our plane. If you want, you can go through and you can multiply everything out, combine like terms, and you can write it in standard form too. Okay, so now that we've got a handle on parametric surfaces and these surfaces that are described by vector functions, now let's talk about area, because the next thing we would like to do is we would like to be able to find the area of these general surfaces, right? These surfaces don't have to be like classic Euclidean geometric objects. They are just functions, right? They are images of functions in space, and we would like to be able to compute their area. So here's how we're going to do it. We're going to reconstruct the mechanics of the Riemann integral again. Again, yes, that's right. The good news is most of the construction is basically identical to what we saw in section 15.9. So I apologize if this is going to be boring again, but you're going to see it's pretty much identical. So if you understood this, then this should go by very quickly. We're also going to restrict ourselves to two-dimensional surfaces just so that we don't need a more general theory of calculus involving differential forms and whatnot. The reason for that is if we wanted to compute the surface area of a hypersurface, for example, we would need to generalize the cross product. So we're not going to worry about that in this class. Some of you can worry about it later when you take a course on differential geometry and such. So here's how we're going to do it. Suppose we have a vector function r that describes a smooth surface S in 3 space. That's the setup. And just for ease, we're going to assume that the parameter domain that R is defined on is a rectangle. So just pretend for a minute that R is defined on this rectangle. Usual deal, we're going to chop it up into smaller subrectangles, R sub ij. There's one right there. We're going to choose one of the corners. We'll just choose this lower left corner, and we're going to label it as U sub I star, V sub j star. So that's our sample point, right? That's like our special sample point. We're just going to choose that corner. Now, under R, under the mapping R, we get what's called a patch. So we're going to take this subrectangle and we're going to map it into space using R, and what we get is a patch. Makes sense because this kind of looks like a quilt. So I don't know if any of you were thinking of that. Maybe you have a quilt on you right now as you're watching this, like snuggling cozily. But this is basically a patch on this quilt. That's what's going on. And the image of this corner here is going to be the corner of one of these right here. So this corner is going to map to one of these corners. Maybe you could ponder and ask yourself why that's the case, but I won't dwell on it now. Okay, so then what we're going to do is we're going to compute the partial derivatives of r at this point. So we're going to call this partial derivative r sub u star. The partial derivative of r with respect to u at this point, at this corner, okay? Same thing, r sub v star is the partial derivative of r with respect to v at this point, just for notations, ease of notation. Now, this should sound very familiar. Now that we have these two partial derivatives, we can approximate that quilt patch with a parallelogram that is determined by these vectors here. Yeah, look familiar? This is exactly what we did back in 15.9. So I won't dwell on this part of the construction. If you want to see why this is the case, I encourage you to go back and watch 15.9, where I go through the whole thing and explain everything there. But this is what it's going to be. These are these two vectors. They generate a parallelogram, and we're going to use this parallelogram to approximate the area of the patch that you see here in blue. What is the area of the parallelogram? It's just the length of the cross product of these two vectors right here. And when you do some simplification, you get this. And so that is giving us the area of that approximating parallelogram here. Now, to get an approximation of the area of our entire surface, we're going to add up all of these parallelograms, one for each one of these patches. And when we add them all up, we get an approximation of the area of the surface. And then, like I say here, you can probably guess where this is going now. So take the limit, make the partition more refined, and we get a definition of surface area that is really, just really elegant. It's very beautiful. So here we go. Suppose you have a smooth surface S given by this vector function defined on some parameter domain D. And we're going to assume that S is covered just once as UV ranges throughout the parameter domain D. So you're not like going back and forth over the surface, right? Just once. Then the surface area of whatever that surface is given by this double integral right here. So it's a double integral over D, and this is the function that we're integrating. And then there's our differential form right there, dA. Like before, r sub u is the derivative of r with respect to u. R sub v is the derivative of r with respect to v. And there's our area formula. Okay. This makes a lot of sense if you think about the construction and why this is actually working, right? So I'm just going to run through it again real quick. These two vectors lie in the tangent plane at any point, and so do these as a result, because these are just scalar multiples of those tangent vectors. So these two vectors lie in the tangent plane. The cross product of those two vectors is going to be orthogonal to the tangent plane. It's a normal vector, right? And then the length of that cross product is the area of that parallelogram that we saw in the previous slide. So this length is literally the area of that parallelogram. So add all of those areas up. Let u and v go to 0, or delta u, delta v go to 0. So let the partition get more refined, and then you get the exact area of S in the limit, as long as the limit exists. Okay. All right, now I want you to try this one. So I want you to try to find the surface area of the cone, z equals x squared plus y squared, where z goes between 0 and 1. All right? So think about it for a minute. Try to imagine it in your head, maybe. Say something out loud about what you're going to do first. And then try to calculate it, and we'll compare answers in just a minute here. Okay, now let's take a look at it together. So we've got the cone here, and we want to find the area. So we have to pick a parameterization. I'm pretty sure I picked a polar or a cylindrical parameterization. Yeah, I really should say cylindrical. Sorry, that should say cylindrical parameterization. So when we do that, we have this parameterization. Z is just R, because this is just equal to R. And then X is good old R cosine theta, Y is R sine theta. And then since we know Z has to be between 0 and 1, that means R is going to be between 0 and 1. And then since we're doing the whole cone, theta is going to go from 0 to 2 pi. So now we have our bounds, the bounds of our integration. So a vector function for the cone is given by this. And now we can compute our partial derivatives, compute their cross product, find the length of that cross product, and so on. So here we go. If we differentiate r with respect to r, we get cosine theta, sine theta 1. If we differentiate r with respect to theta, we're going to get negative r sine theta, r cosine theta, and 0. Now let's cross them, compute the cross product. So there are two vectors, go through that cross product process, and we get this. So this is a normal vector to the curve, or sorry, a normal vector to the surface at every point. Now we can compute the magnitude. So if you compute the magnitude of this vector here, you get some nice simplification. Cosine squared theta plus sine squared theta is just going to be 1. So what you end up with is r squared plus r squared, which is 2r squared, which simplifies to this. There it is. Now we have all the pieces. Now we can compute the integral. Here we go. So using our formula, we're just adding up the magnitude of those cross products at every point, transferring it into our cylindrical coordinates. We're going to get this, just like so. Here, notice that the extra factor of r is not included because this actually includes that extra factor of r. This is why section 15.9 is so important, because this is actually just the determinant of that Jacobian, you could say. But I won't go into too many details there since I already did that before. But that's why we're getting this result right here. Now we've got a pretty simple integral to evaluate. We can do it iteratively by Fubini, and when we simplify, we're going to get root 2 pi. Boom, there it is. Now, before we go to the next bit, I want to show you how to do it in Mathematica. So let me pull up Mathematica here. Here we go. And I took the liberty of just plotting an image of the cone as well. This is the thing that we just found the image of. I'm sorry, the area of right here. There you go. So this is the cone. R goes from 0 to 1. And here is the plot. So I used a parametric plot 3D command. R cosine theta, R sine theta, and then R. Those were our parametric equations, right? R goes from 0 to 1. Theta goes from 0 to 2 pi. Oh, just a quick reminder, if you want to get this theta letter, you can type escape theta escape, and then it will give you this actual theta symbol. So this plots the graph, and then this is the formula to compute the area. So it literally is simply just area. I'll talk a little bit more about it at the very end of the lecture, but this is the area command. So we put in our vector function, and then we put in the bounds for our parameters as well. And then we run it, and it gives us the area, root 2 pi, just like we had in the slides. So Mathematica can do this too. All right, now let's go back to the slides. Now that we have this general formula for surface area, now we're going to recover that surface area formula from the section that we skipped. So we skipped section 15.5. Here is why. Because now that we have this more general formula, we're going to get it for free. So suppose our surface S is described by a function of two variables, z equals f of x comma y, where x, y lies in D, and f is a C1 function. Then a vector function for this surface is given like so, x, y, f of x, y. Compute our partial derivatives, r with respect to x, r with respect to y. Remember, this is the partial derivative of f with respect to x and the partial derivative of f with respect to y. Compute the cross product, and we get this right here. This is actually going to be the outward normal vector to that surface right here. This is what it's going to be, right? But now that we have that, we can compute its length. So we compute its length, and luckily the length is going to be very nice. It's going to be this partial squared plus this partial squared plus 1. I'll leave that to you to verify, just using this right here. Find the length of that vector. And then we get this expression here. It doesn't really matter which order you write these terms in the radicand. I just did it both ways so that we can do some structural comparisons. But this is the length of that cross product. So if we want to know the surface area of a function described as a function of the variables x and y, this is the formula. There it is. So again, we are just adding up. Adding those values up, just like we were before, except now we have an explicit form of this area function. There you go, of that magnitude, the magnitude of this thing right here. All right, that's it. So one cool thing about this is take a look and notice the similarity of this function, or this area formula, to the arc length formula that you learned in Calc 2 or Calc 1, depending, right? They're very, very similar, right? Very, very similar. And the reason for that is because surface area is kind of like the next step up from arc length, right? So the formulas are very, very similar. You pretty much just have an extra term in there to account for your second variable, right? Like if this weren't here, you would just have the good old arc length formula. There it is. So the structures are very similar, right? What's also cool about this, I don't know if you remember this, but if you remember the formula for the area of a surface of revolution from Calc 2, possibly Calc 1, it was this one. So you got to kind of dig way, way back into your older calc experience. Remember it was 2 pi r, and then this was the length of the curve? The way that I always explain it is uh, 2 pi r is giving you that rotation, because 2 pi r is the length of the circle, the circumference of the circle. And then this was the arc length of the curve that you were rotating around that circular path. So you do like the length of the curve times that circle, add it all up, and that gives you the surface area for that surface of revolution. So what I'm claiming is that we can actually recover this formula now as well using that formula from corollary 1, using this formula. So we're going to recover it right now. That's corollary 1, right? Yeah, we're going to do it right now. So again, the surface area of revolution formula that you learned, you could have skipped it back in Calc 2 because we're going to get it right now. But not everybody takes Calc 3, so oh well. Here we go. Here is the proof. Suppose that our surface S is generated by rotating the curve y equals r of x about the x-axis. We're just going to assume that r of x is greater than 0, so we don't have any issues with the rotation. We're going to integrate from x. We're going to integrate with respect to x from a to b, and then this is our vector function. So just like we had earlier, right? I forget which slide it was. X, r of x cosine theta, r of x sine theta, using that right triangle trigonometry. Compute our partials. Now we compute their cross product. Here it is. So I'll leave those calculations for you to go through and check. But this is what you get when you compute that cross product. Now we're going to take the length, or the magnitude, using our good old distance formula. Gets a tiny bit messy, but just stay diligent, keep moving forward, and then it will simplify nicely. This is going to become this. There we go. This will simplify to just r of x because we assumed that r of x was strictly non-negative. So the absolute value just becomes the function itself. And there it is. Now we're going to use our formula. So our area formula says we need to do this. Add up the length of all those cross product vectors at every point. Here we go. X goes from a to b. Theta goes from 0 to 2 pi. Now, this function doesn't depend on theta, the integrand, so we can split this up into two separate integrals and compute them separately. The integral with respect to theta is just going to give us 2 pi. And then this is actually the integral we wanted to retain, right? So let's just throw 2 pi back in there. Get that, and boom. That is our area formula. So we got that one for free as well. How cool is that? I think it's pretty cool. Okay, so last but not least, some helpful Mathematica commands. I'll show you one other one. We already took a look at them earlier in the lecture. So the first command is the area command. This finds the area of a two-dimensional region. In our case, it's just used when the vector function is a two-variable function. All the examples in this section were two-variable functions. There's another command you can use that's called the surface area command. This one finds the surface area of a three-dimensional region. So if you've got something that is described using three variables instead, you can use this command. That's pretty much it. What's nice is both of these commands allow you to input an implicit region. So you can basically describe a region using inequalities, and you can plug that in and say, okay, compute the area of this implicitly defined region. Or you can do like we did a moment ago, and like we're going to do in a moment here. You can just plug in the parametric equations or the vector function itself. So one other Mathematica example here, and then we'll call it a day. This one we saw. The other one I was going to show you is this one. So here is where we plotted that sphere using our spherical coordinates, right? Well, now I'm going to ask Mathematica to find the area, the surface area of this sphere. So because we only need two parameters to describe this, we can just use the area command. So I just plugged in the same vector function right here, specified the bounds for our parameters, and then had it compute it. Boom, there it is. And this makes sense. So if you don't remember, the surface area of a sphere of radius r is 4r squared. So in this case, r is equal to 1. So our area is 4 pi times 1 squared, as expected. Hooray! So this is a good way for you to check your work. So if you're doing the homework and you compute an integral and you want to see if it's right, you can throw your formula or your parameter your parameterization into this area command and then see if you got it right. Okay. Now, what is left? Time to play. That's what's left. I'm excited to work with you on this particular activity. We're going to go to the computer lab. We're going to plot a bunch of these surfaces. We're going to look at grid curves and identify which curves are fixed and which curves are not. So it's a really, really fun one. But on that note, I won't ramble anymore. Thank you again for watching, and I will see you all next time. Soon enough. Sometimes it takes a minute to get these things set up. Right? Okay, there it is. Take care. Bye.